According to the National Electrical Code, specifically Article 250.104, a building's electrical system must be grounded to a metal water pipe if it is available. This is because metal water pipes offer a low resistance path to the earth, which aids in safeguarding the electrical system against lightning and other electrical faults. The availability of the water line is key, and the code does not specify its exact location, only that it must be present. In this scenario, the presence of a water line at the fence, regardless of whether it branches from the main water supply or the irrigation system, necessitates its use as a grounding electrode. Therefore, it must be connected to the grounding electrode conductor, often referred to as the GEC, of both the main panel and the subpanel that serves the addition. This connection guarantees that both electrical systems adhere to the NEC requirements for proper grounding, thus ensuring safety and code compliance. To delve deeper into the specifics, let's consider the components involved and how they interact. Firstly, the grounding electrode conductor, or GEC, is the conductor used to connect the grounding electrode to the equipment grounding conductor, the grounded conductor, or both, at the service equipment or at the source of a separately derived system. Its size is determined by NEC Table 250.66, based on the size of the service entrance conductors. Secondly, the grounding electrode system consists of all electrodes that are present at a building or structure. This system can include items such as metal underground water pipes, metal frames of buildings or structures, concrete encased electrodes, ground rings, and rod and pipe electrodes. The NEC outlines specific requirements for each of these electrodes, including their size, installation depth, and connection methods. Thirdly, a metal water pipe electrode, as covered under NEC 250.52a, requires that the metal water pipe be in direct contact with the earth for at least 10 feet. It also mandates that the metal water pipe electrode be supplemented by an additional electrode, such as a ground rod or ground ring. This supplementary electrode ensures that there is a redundant grounding path in case the water pipe becomes non-conductive or is disconnected. Now, let's address some potential scenarios and questions that may arise during the grounding process. One common question is what to do if the metal water pipe is interrupted by an insulating fitting or coupling. In this case, the grounding connection must be made on the street side of the insulating fitting to ensure that the entire length of the metal water pipe is used as an electrode. Another question is whether a plastic water pipe can be used as a grounding electrode. The answer is no, as plastic pipes are non-conductive and cannot provide a low resistance path to ground. In such cases, an alternative grounding electrode, such as a ground rod or ground ring, must be used. Furthermore, when connecting the GEC to the metal water pipe, it is essential to use appropriate fittings and connectors that are listed for grounding purposes. These fittings must be made of corrosion-resistant materials to prevent deterioration over time. The connection should be made in a location that is accessible for inspection and maintenance. It is also important to protect the GEC from physical damage by running it through conduit or other protective means. Let's also consider the specific requirements for the subpanel serving the addition. The subpanel must have its own grounding electrode system that is separate from the main panel's grounding electrode system. This is because the subpanel is considered a separately derived system and must have its own grounding reference. The grounding electrode system for the subpanel can consist of the same types of electrodes as the main panel, such as a metal water pipe, ground rod, or ground ring. The size of the GEC for the subpanel is determined by NEC Table 250.66 based on the size of the feeder conductors supplying the subpanel. It is critical to ensure that the grounding electrode systems for both the main panel and the subpanel are properly bonded together. This bonding helps to equalize the ground potential between the two systems and prevents voltage differences that can create safety hazards. The bonding is typically accomplished by running a bonding conductor between the grounding electrode conductors of the main panel and the subpanel. The size of the bonding conductor is determined by NEC Table 250.102 based on the size of the largest ungrounded conductor supplying the subpanel. In summary, the NEC mandates that a metal water pipe be used as a grounding electrode for both the main panel and the subpanel, provided that it is available. The grounding electrode system must comply with all applicable requirements of the NEC, including the size and installation of the GEC, the type and location of the electrodes, and the bonding of the grounding electrode systems. By adhering to these requirements, you can ensure that the electrical systems are properly grounded, which will protect against electrical shock, reduce the risk of fire, and enhance the overall safety of the installation. In addition to the technical aspects, it's essential to understand the practical implications of proper grounding. A well-grounded electrical system provides a stable reference point for voltage, which helps to minimize electrical noise and interference. This can improve the performance of sensitive electronic equipment and reduce the risk of data loss or corruption. Proper grounding also helps to protect against transient voltage surges caused by lightning or other electrical disturbances. These surges can damage or destroy electronic equipment if they are not properly diverted to ground. A well-grounded electrical system provides a low-impedance path for these surges to follow, which helps to protect the equipment from damage. Furthermore, proper grounding is essential for the operation of ground fault circuit interrupters, commonly known as GFCIs. GFCIs are designed to detect small imbalances in the current flowing through a circuit and to quickly disconnect the power if a ground fault is detected. A ground fault occurs when current leaks from a hot conductor to ground, which can happen if someone touches a live wire or if there is a short circuit. GFCIs are required in areas where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor locations. Without proper grounding, GFCIs may not function correctly, which can increase the risk of electric shock. Moreover, the periodic inspection and maintenance of the grounding system is essential to ensure its continued effectiveness. Over time, grounding connections can corrode or loosen, which can increase the resistance of the grounding path. This can reduce the effectiveness of the grounding system and increase the risk of electrical hazards. Regular inspections should include a visual examination of all grounding connections to look for signs of corrosion or damage. The resistance of the grounding system should also be tested periodically to ensure that it is within acceptable limits. If any problems are detected, they should be corrected promptly to maintain the integrity of the grounding system. Additionally, it's important to consider the impact of any modifications or additions to the electrical system on the grounding system. Any changes to the electrical system can affect the grounding path and may require modifications to the grounding system to maintain its effectiveness. For example, if a new circuit is added, it may be necessary to upgrade the size of the grounding electrode conductor to accommodate the additional current. Similarly, if a new piece of equipment is installed, it may be necessary to add a supplemental grounding electrode to ensure that the equipment is properly grounded. Remember, proper grounding is not just a matter of code compliance, it's a fundamental safety requirement. By following the guidelines outlined in the NEC and by performing regular inspections and maintenance, you can ensure that the electrical systems are properly grounded and that the occupants are protected from electrical hazards. And also make sure that the water line is metallic. In addition, the NEC mandates equipotential bonding in specific locations to minimize voltage differences and prevent electrical shock hazards. This is particularly important in areas such as swimming pools, hot tubs, and agricultural buildings where the risk of electrical shock is elevated. Equipotential bonding involves connecting all metal parts that are likely to become energized to a common bonding grid. This grid helps to equalize the voltage potential between these parts, which reduces the risk of a person contacting two different metal parts with different voltage potentials and experiencing an electrical shock. The NEC provides detailed requirements for equipotential bonding in specific locations, including the size and type of bonding conductors, the methods of connection, and the areas that must be bonded. It is essential to follow these requirements carefully to ensure that the equipotential bonding system is effective in minimizing electrical shock hazards. Furthermore, surge protection devices, often called SPD, play a vital role in protecting electrical equipment from transient voltage surges. These surges can be caused by lightning strikes, power grid switching, or internal equipment faults. SPD are designed to divert these surges to ground, preventing them from damaging sensitive electronic equipment. The NEC requires the use of SPD in certain applications, such as dwelling units, commercial buildings, and industrial facilities. The type and location of SPD should be selected based on the specific application and the level of surge protection required. SPD are typically installed at the service entrance and at downstream panels to provide comprehensive surge protection throughout the electrical system. The effectiveness of SPD depends on proper grounding. SPD rely on a low impedance grounding path to quickly divert surge currents to ground. If the grounding system is inadequate, the SPD may not function correctly, and the equipment may still be damaged by surge voltages. Therefore, it is essential to ensure that the grounding system is properly designed and maintained to maximize the effectiveness of SPD. Finally, remember that working with electrical systems can be dangerous if you are not properly trained and equipped. Always follow safe work practices, wear appropriate personal protective equipment, and consult with a qualified electrician if you have any questions or concerns. Electrical safety is everyone's responsibility, and it is essential to take the necessary precautions to protect yourself and others from electrical hazards.